Now I want to demonstrate my development tool for digital filters in Windfc. One module of this can do the last both conversions with a computer module. Yeah, simulation. No, the example in Windfc. There I want to show also the Bode plot comparison. Because in this program I can also display digital and analog filter Bode plots. Okay, let's go to the program. If I open it, first I want to type in the analog filter. You have two possibilities. One possibility is this button, the UFK button. In the UFK button you can type in a polynomial function with p. Yeah, here the coefficients are called C and D. Delay time is also allowed, so you can here just type in the coefficients of the numerator and denominator starting with 0. 0 is the coefficient without a p. Yeah, behind the button factorize, this program can calculate the zeros and poles and check stability, and then you can copy the result into that, what I want to show you now, the analog filter function. This button can display the filter functions within, jetzt kann ich das nicht aufschieben, in a form which can be seen. Sorry, I want to shift it down. Area is not large enough. You see the transfer function of FMP here can now be typed in the form, as I say, time constant form. Yeah? Either in numerator or in denominator modules, which carries real zeros and real poles, and this is the form of a second order function which can be displayed for conjugated complex zeros, and here conjugated complex poles. Again, you can have a delay time. Here you see in this region you can type in the number of real zeros, real poles, complex poles. Here the program expects a DC gain. Here you can add a delay. And here then this grid opens then the possibility to type in the coefficients. In our very simple case we have one real pole, and here you can type in the time constant. Our time constant was 0.5. And the gain of our simple PT1 is 2. So now we can leave this window with the close button, because now this filter is stored. You can save the coefficients. You can, we make later, draw Bode plots. But first I want to show you the design of a digital filter. Here you type in the time constant form. With this button I previously have shown, you can convert any polynomial form into this time constant form. Okay, I close this window and start now with the design of a digital filter. This is behind the button A to D. Yeah? A to D opens a module which just waits for selection of rectangular trapezoidal approach. Note, this is that what we just have discussed. So first I want to start with a rectangular approach. This is a delay time, and these three fields are just information fields, because if you set the delay time to 0.1, of course then the sampling frequency is 10 Hertz and the Shannon frequency for signal transmission is half of the sampling frequency, so up to 5 Hertz sinusoidal signals you can have no aliasing. And these are the radian frequencies just multiplied these values with 2 pi. Okay, doesn't matter, you just type in the sampling time, click on the button, with a green arrow. That means now the result is stored in our digital filter window. That is this button. Behind this button now you can look into the coefficients, set some parameters for Bode plot drawing, and finally you see here a real-time digital filter box down to 1 millisecond with any good computer, any PC, any Windows PC. You can work with a real-time filter. Yeah, it's not so fast. Yeah, 1 kilohertz sampling time is not so large, but for slow systems this works very good. Look for the numbers here. B1 and A1 are the names for the filter. I also want to give you the information that the form of transfer function now looks like this form displayed in the bottom of this window. That is the transfer function, FFZ, and the polynomial function is written with z and negative exponents. But note that here the name of the letter for the coefficient is not Q but B, and here the letter for the denominator coefficients are now A and not P. That is a very simple reason. For a general digital filter it is common to use A and B. For controller transfer functions it is common to use Q and P, as I have done in our previous lecture. Note, very important, the traditional form for a digital filter with A's and B's carries here a plus sign. So a minus sign is hidden in a coefficient. Let's compare now the result with our paper. This is the rectangular approach. As a B of 0.33 repeated and an A with negative 0.833 repeated. Quick look. I've shifted back my writing to a rectangular approach. Our filter is calculated at this position. Here you see Q0 is 0.3 repeated and P1 is positive 0.8 period, because the minus sign in the normalized form here is explicitly drawn in the normalized form of F. So in the controller case it is common to write 1 minus coefficient by z to the power of minus 1. In the filter form it is common to write 1 plus a1 times z to the power of minus 1 in the denominator form. So be careful with the minus sign. Sometimes it could cause problems, but I just do the same thing like many books, so what should I do? Okay, what can we do now with my digital filter? We can store the coefficients, draw Bode plots, we will do later. I just close this window and open a new one with which we can calculate now step responses. This is the step response button for a digital filter. If I click on this button, you get a window where you can set the input value. Yeah, if you have a unit step, you get all ones. If you have a unit impulse, you get here a 1, rest zeros. Or of course you can type in any function you want to have. Yeah, so I of course want to have a unit step. Sampling time comes directly from the filter. Here you can decide how many steps you want to have. Here you can save, load and store this step function. And here you can now calculate the output value. Note there are two selection possibilities. One with a simple display and one with steps. Yeah, you can decide to see the real sample and hold curve if you click on steps. Yeah, and with the draw button, this window is closed and you see the drawing in our chart display in the main window. Yeah, that is the resulting curve. I should add the analog PT1 curve. This cannot be calculated with this tool. It is not prepared. There is no module to calculate analog step responses. In this window, I can only do analog step responses in Rec+C#, that is the analog simulator. So what I will do is I stop the program, produce this step response with Rec+C# without showing. Why not should I show this? Why not should I show this? So I just open Rec+C# and produce the step response, which I can load here. Note we have a 2-second time area, so I open Rec+C#. Why not do with my screencast program? Switch to English text. Just I click this box. The PT1 should have the gain 2 and should have the time constant 0.05. Say OK, we need one branch. Click, click, and we need the step response with time 2 seconds. Input sample amplitude 1. We have only one block, one input, no problem. This is the analog PT1 step response. And I want to store this curve now as an ASCII file to export here and import in my other program. So that's a connection. The connection of data goes via an ASCII file. So I store this, and it's the import button. Sorry, this is natürlich wrong. I want to have the store button here. This button opens the possibility to select a file name. I just write PT1 step response. So I click on store and I can close this window and close this simulation and go back to my this program, and now I can load this curve via this data button. You see, in both programs I have set the folder. This was prepared just in one step. All things here, all parameters in the load file box can now adapt to some other types of curve. The default setting fits, of course, to my curve. So if I click on display, then you see now the red colored PT1 step response, which I have just produced in Rec+C#. So you see how fast this works. So why should I add a module here if I have the second program and can very easily produce this type of curves? Okay, this is the rectangular approach. We have talked about the fact that the trapezoidal approach is a little bit better. So let's check how we do this. Very simple. Just go back to the conversion module. Select the trapezoidal radio button. Click OK. Look into the digital filter window, and here you see now the coefficients of my trapezoidal filter form of my PT1. Just go back to my writing to compare the numbers. Note we have two Qs, Q0, Q1, which has 0.18 repeated, and one P, which has positive 0.81 repeated. In my program, you see here both Q0, Q1, B0, B1 is the same name, but here the negative sign now is covered with the coefficient named A1. Okay, this is a filter. Now with trapezoidal design, I close this window, open the main window, go back to this curve, this module, click on calculate output, and now draw the curve. And here you see now, 3 curves in one diagram is not so good. Of course, I can now show the blue curve was my rectangular, and the green curve now is the trapezoidal approach. I can make the curves a little bit thicker. This is helpful, I don't know. These are exactly the same curves which you can see in my paper. What we can do more here is we can display the border plots. Border plots and compare now the analog filter with the digital filters via using the frequency response. This can be done. I delete now all curves because border plot has a totally different scaling. I delete all curves with this button. I first start with analog border plot. This is possible with this program. You have to select start and end frequency. Here omega starts from 0.01, goes to 100. We see 4 decades. You can change these numbers. Here you can also type in frequencies in hertz if you want. How many points you want to have. It's 3. So just I click on the magnitude button or the phase button depending on what I want to see. I think here it's the best to show you the magnitude curve. So I click on this point and we see now the border plot with fine grid. You can see that I have really a logarithmic scaling, 0.1, 0.01, 0.1, 1, 10, 100, 4 decades over the whole region. We see now the typical PT1 border plot. Here with constant gain 6 dB, it is a dB scale here, 6 dB, and here with a corner at omega is 2, and then with a minus 20 dB over a decade decrease. And first I want to show you the border plot of the rectangular filter, so I have to go back to the calculation of the rectangular form, say OK. Look if this filter just is available here. Yes, it is. Same parameters, the default values are fitting. So I think I just click on F magnitude and then you can see the magnitude curve of analog blue and digital red filter curve. Okay, look what happens here. There's a big difference in this region. Here we have good coincidence up to say 10 to 20. But here, of course, then we have a problem, a big difference. That is simply said, that is here the frequency of, we have sampled with 10 Hertz. This is a frequency 10 Hertz. That is omega axis here. So we have here in this position the 10 Hertz, and rather roundabout here we can define the Shannon limit where we reach a limit where we can use this filter up to this point, and here we have aliasing with not recoverable input signals. So you see the first beginning it is not bad. Okay, let's go to the trapezoidal form. I click on trapezoidal, say OK, go here into this diagram and click on magnitude button for the trapezoidal form. Now you see the green curve. The green curve fits very good up to this part, but then this goes down. The red curve, rectangular, goes up, trapezoidal goes down. A typical behavior of a trapezoidal curve is that at Shannon limit, here at 5 Hertz, radiant frequency is 31. At 5 Hertz we have 0, so the gain is 0 or negative infinite dB values. Now these are dB values, it's a border plot. And the behavior at at this point is the same. So yeah, we can just look if which filter fits better in the region of omega 10. We have a cursor function to show this. I can enlarge this a little bit, and then you can see the green and blue and red curve are nearly identical up to the 0.10, but here they are a little bit different. So no big difference up to high frequencies, but if you reach the channel limit, of course, then you have totally different behavior. Yeah? You can use a digital filter only for frequencies which are much lower than sampling frequency. That's all. Okay, so far. Okay, this is a point where I can show you finally a very large advantage of digital filters. Yeah, here you see the green curve. I delete all other curves and I draw back the magnitude curve, which is internally stored. You see the now only the magnitude curve of the digital trapezoidal filter. And what I want to show you is now if you want to have different corner frequencies like this, it is very easy to change in a digital window to change the corner frequencies, because the design sampling frequency and the runtime sampling frequency could be different, because you can now select the runtime sampling frequency. I make this with a factor of 2 smaller. I go to 50 millisecond instead of 100 millisecond. What happens with the filter function? If I click on this, you see a new filter function which is shifted now by a factor of 2 to the right position. So this is exactly the same curve like the blue curve, but there is just a frequency shift. So in other words, with the selection of the runtime sampling frequency, which is just one parameter in your hardware of a digital filter, you can shift your digital filter curve to any position. Furthermore, here you can work with the real-time digital filter. Of course, you need an ADC module. With a hardware simulator, of course, you cannot see anything. It's senseless, yeah, to work a filter with the hardware simulator. So here you have to buy or select a real hardware for an ADC card. Then you can activate this filter and run this filter, and then your ADC card, so analog input and digital output, gives you the possibility to use this filter really with signals. But of course I cannot show this in a system where I have no ADC card, like now at home. Okay, so far that covers completely the chapter 7.3 in the paper, and yeah, now comes the chapter 7.4. We go back to control systems and use now all these methods and now to improve our PID design.